So let's see how we can use the definite integral to derive the formula for the volume of a cone of radius r and height h. So here is our cone. It has a radius at the bottom or top. If you do it upside down, you get the same thing either way, of little r, and its whole height is h. Alright, what we're going to do is we're going to put in a slice in here, an arbitrary slice, and we're going to see what's happening with that slice. So there's our slice, and to make this, let's give it some labels. This slice, let's say its radius, just to keep it from getting too confusing, instead of using r, let's say that radius is x sub I. I use the sub I to note that it varies. It would be a different radius depending on where I found it. And the distance that slice is from the top, I'm going to call, now let's not use h actually, same issue. Let's use y sub I, and therefore our slice has a thickness of dy. Alright, so the next thing we do is we find the volume of that ith slice. Well, again, we choose the slice so we can assume the sides are straight up and down. So our slice is actually just a cylinder, not a cone. So for a cylinder, we have pi times the radius squared, which is x sub I squared, times the height, which is dy. Now, what we're going to want is a relationship between x and y to get these variables matched up. Well, if I look at my cone directly from the side to kind of see what's going on, if I split it in half, I've got r here and h here, and then here I've got x sub I, and here I've got y sub I. So we have similar triangles because we got a triangle inscribed inside another triangle. So their ratios will be equal. So x sub I is to y sub I as r is to h. Now my goal was to sub out x sub I and put y sub I in, so I'll cross multiply the y sub I, so I get x sub I equals r over h y sub I. And it's important to keep in mind here, r and h are just constants. They're not variables. They're something that would be given in the original problem. So we have pi, and now we're going to sub that in, r over h y sub I squared dy. And I'm going to simplify a little bit. I have pi r squared over h squared y sub I squared dy. That's just squaring everything that's in there. And so when I go to write my definite integral for volume, this is all a constant here. So I don't even need to put that in my integral. R squared h squared. Start off my integral, I'm going to have y squared dy. I don't need a sub I here because I'm now in the continuous case. And now let's think about how y will range. And this is whether we're measuring it from the top or from the bottom. If we're at the very top, y is going to be 0. And if we're at the very bottom, y is going to be a maximum value of h. So there are our limits. So I have pi r squared over h squared. This guy here is going to become y cubed over 3, because we do need to take the antiderivative from 0 to h. So we get pi r squared h squared. We're going to plug in that h. We get h cubed over 3. If we plug in 0, that zeroes it out, so we don't really need the other part. Oh, and I lost my square there. H squared. The h squared is going to cancel out 2 of those. So if you look at what we got, we have pi r squared h over 3, or writing it in as a more familiar way, we see it for a cone a lot of times, pi over 3 h r squared, or pi over 3 r squared h. And there's the volume for a cone.